So, many of you might be wondering, maybe once in your life, how pi, the circle constant, was able to be so accurately measured. After all, it's an irrational number. The number of digits it has goes on until infinity, 3.14159.265 until infinity. I mean, in order to get an approximation of what pi is, we could just maybe try to measure the circumference as accurately as we could, and then divide it by the diameter, and then we could see what we could get. But this is only going to be accurate to maybe 10 or 15 decimal places, and we've been able to calculate pi into the millions of digits. And I don't think that there's a machine that we have that could measure the circumference of a circle so accurately as to produce millions of digits. So how is this possible? Well, the answer is through Taylor's theorem. Brooke Taylor was a British mathematician who made Taylor's theorem, and what Taylor's theorem says is that any non-polynomial function can be approximated by using this method, taking the original function at evaluated at the interval of convergence, which I'll explain later, and you add on these values to it until the which involve the derivatives. So if we take the function evaluated at a plus the derivative of f evaluated at a times x minus a plus all this until we get to the required derivative or value that we need in order to accurately display this as much as we want. So, what does this mean though? What is the interval of convergence? Well, the interval of convergence is like this. Let's say that I had a graph of e to the x. E to the x is a non-polynomial function, and e is another example, just like pi, of an irrational number that we know of millions of digits today. So let's see how scientists might have been able to get that. So here's the coordinate plane, and here is e to the x. Or at least it's supposed to be e to the x. Oops. Okay, e to the x. So this is what looks like a function of e to the x. So let's say that I chose one area along this graph of e to the x, and this is any x value, any arbitrary x value. I'll call it x equals a right here to match up with the definition of Taylor's theorem up here. So what this means is that it's an approximation. Taylor's theorem is supposed to produce a polynomial which will accurately approximate but not equal the non-polynomial function such as e to the x, which is being approximated right here. So because it's an approximation, the approximated graph cannot entirely be y equals e to the x, which is the actual graph. It has to be different because it's only an approximation, but similar enough that we could get similar answers by plugging in values into the approximation. So what this means is that if I have x equals a, then this function, the approximation of Taylor's theorem, is going to equal the actual function y equals e to the x only at this point, because this is the point which the polynomial will pass through in order to emulate this actual graph as best as possible. Because it's only an approximation, it can only intersect once, and that once is going to be at x equals a. And if x equals 0, which is what many functions do, which is what many published Taylor series of functions do, because they usually simplify things greatly. These Taylor series are called Maclaurin series when they're centered at 0, where a equals 0. So let's do an example. Let's evaluate y equals sine x. Sine is a function. It's a non-polynomial function, which, as most of you know, oscillates between -1 and 1. It takes an x value and produces a y value that's between -1 and 1. So what we need to do is, if we want to take a second degree, or which is only until squared, Maclaurin version of this, or Taylor series centered at a equals 0, then we would say f of x, or sine x, is approximately equal to, because it's only a second degree, approximately equal to sine of 0, because sine is the original graph, plus cosine of 0, because cosine is the derivative of sine, and x minus a is 0, so this just becomes x, plus f double prime, which will be negative sine 0 times x squared. So what will this be? This will mean that sine of x is approximately equal to sine of 0, which is 0, plus cosine of 0 times x, which is x, minus sine of 0, which is 0. So we have here that sine of x is approximately equal to x. So this might look weird, but at small variations, and this is actually extremely important in physics, it's called the small angle measurement, is that sine of x is approximately equal to x at very small values where it's near 0. Because we only took the second degree, which means that we could go on until infinity and become more and more accurate until we actually get the original sine function. But since we can't, we only have x. And this x is technically the second degree sine Taylor polynomial for the sine function, because sine of 0 is 0, and x squared times 0 will just become 0. So sine of x here equals x. Now if you wanted to continue this, then we would probably get something like x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial plus so on and so forth, because sine and cosine, negative cosine, the derivative of negative cosine is just sine, which means that this will continue repeating and repeating until we get that the equation, or the Taylor approximation for sine of x, equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on and so forth. Now, many of you might be wondering why I began this episode with pi, when this was talking about functions. Pi is a number. But remember that arctan, for example, arctan of x is also a function that's not a polynomial, and because it is a function, so f of x equals arctan x, it can be approximated using this. So then if we use a high enough approximation, and you know that in radians, arctan pi equals 1, arctan 1 equals pi, my mistake, arctan 1 equals pi over 4, then we can approximate 4 arctan 1, or we can take this entire series for arctan and plug in 1 for x, and then we can multiply our result by 4 in order to obtain an approximate value for pi. So computers are very much capable of knowing x minus a to the 1000th power. So by plugging in these